Hi everyone, welcome to another one of my conference presentations. This one takes us all the way back to 2011. I presented this paper at both the Engineering Technology Forum and also at the Australasian Transport Research Forum. So there's some changes between the two presentations. I got this one here. I sort of cut it down a little bit. I also don't have the logos on there, so I'm not sure which version it is, but I'll just play through the slides anyway. So by the way, the title of this paper is actually Advanced Methods of Evaluating Benefits from Improved Flood Immunity in Queensland. So why do we need to look at flood immunity? Well, back in around 2011, Queensland experienced some of the worst floods in history, and there was plenty of closures of roads throughout the state, and even Brisbane was hit pretty bad with the river flooding and closing down parts of the city for up to about a week. And this was actually the paper I was doing this was actually around that time. So when it came out in the conference, it was actually sort of ideal to address a problem that was quite apparent anyway. And with current cost-benefit analysis work, not much has actually gone into looking at flood immunity benefits of upgrading roads and what approaches should go about doing it. So this paper was really trying to fill a gap in at that time when it was actually quite in high demand. And there are a number of other agencies as well that were looking into flooding. So it was quite a critical piece of work that really needed to be done. So what we've got here in this, what we call that histogram, 3D histogram it is flooding data for a number of rivers within Queensland, Australia that is. And so you can see this is not the road closures per se, but this is the times when these rivers are actually flooded. And roads within that vicinity would be flooded as well. We didn't actually have data on all the closures. The data for that was quite poor, but instead it took a look at the number of rivers that were flooding and when those floods occurred. So we got data from 2000 all the way up to 2010, and we took basically the worst rivers and what they were. So we got, what was that? We got Cooper Creek, Tully River, Barco, Horton, and a number of other ones you got data here for. We actually have a better look at that in the paper itself. It goes into a little bit more detail on this flooding data and how I actually used it. So let's take a look at some of the projects that are actually being proposed around this time. So we got this table here, and this is not actual projects, but this is the regions and the costs, the capital costs that are actually being proposed for some of the upgrades to some of the sections of road that were getting flooded and some of the bridges that were closing regularly or actually getting even knocked down and badly damaged. In fact, a lot of this is actually repair work, and that's actually part of the disaster relief recovery arrangements. Actually, federal funding was being provided for these damaged bridges and roads, but only to repair standards. As you can see, we've got actually got a list there of the projects. So some of them regions like far north, where it tends to flood quite a bit, you've got 15. Northwest, another one with about 16. Mackay and Whitsundays, not so far north, but still quite a few projects being proposed there. And the capital costs are altogether in excess of 100 millions, just talking about repairs. We're actually going to be talking about here is actually improving flood immunity, which wasn't so much on the cards at this time. This is 2010. This is before we had all the major flooding events and all. So I think a few things had changed since then. A big problem when you're trying to evaluate a flood project is that the benefits tend to be quite low. And that is mostly because the areas that are getting flooded are areas typically either further out west in Queensland where you've got a lot lower populations, or further up north with the same thing. You have the lower populations and you have the lower traffic volumes. And if you have a lower traffic volume, then you need quite a considerable number of benefits per vehicle using that. And existing methods that are used are very much based around the number of vehicles within that area. So you've got more vehicles in the area, the higher the benefits. And for areas that have quite high traffic volumes, the flood immunity is generally reasonably good. So you don't have so many projects down in those areas. But you've got areas that are further out west where communities potentially can get cut off for several months at a time. But using fairly traditional cost-benefit analysis approaches, the benefits are just not there to cover the costs. So again, you could be talking about benefits that are not being sufficiently captured, or maybe we're talking about costs that may be a little bit too high. But that's something that we're investigating as part of this paper. So when we talk about benefits typically included in a cost-benefit analysis for road or transport projects, we're generally looking at things such as reduced travel time costs or travel time savings, vehicle operating costs, which includes like reduction in fuel consumed or reduction in wear and tear of vehicles and tyre wear. We also look at reduced maintenance on the roads and all. You get a new road, doesn't require so much maintenance because it's new. And also accidents as well, or crashes. So you upgrade a road or improve the alignment and stuff like that. The road, you typically would expect it to be safer and you'd have less fatal crashes or serious accidents. So these are what is typically included in your cost-benefit analysis. And a lot of that is what I mentioned just now, revolves around the number of vehicles. So how are we going to look at it, and how we're going to look at this a little bit differently? I'm going to get into that in a few moments. So what benefits are typically not included? So there's certain benefits in relation to maintenance and stuff and repair as well. Like when a bridge gets knocked down by strong currents, for example, from a river, there's going to be repair costs and all of that. And sometimes that is not always incorporated. And it's not just the repair costs of the bridge, but it's also the disruption to activity caused by that. And if a bridge is down for long enough, certain activities may not go ahead whatsoever, or they're going to get delayed. And also depends as well what alternative routes can be taken. For example, many areas in northern Queensland and further in western Queensland, there actually maybe only one or two routes, and those routes may actually be cut because of the flooding. So again, that's where we look at the network, and you look at the network, you're actually going to pick up more benefits for actually upgrading roads and improving flood immunity. But it's knowing what roads should be fixed and which roads are particularly critical when it comes to access. And again, that's another one as well, the cost of access and loss of access. Loss of access for any substantial amount of time can actually be very costly, especially if it results in people not receiving medical treatment. It could be where produce expires and got fruit and things like that going bad. And even, daily things like, even things like water supply and stuff like that can be affected if there isn't actual access and all. And also in the long run as well, you may have lost productivity because there's a lack of confidence in that area if there's frequent flooding and long closures. So all of these costs generally don't get picked up in your cost-benefit analysis. So in order to pick up these benefits, typically you're going to need data. And some of this is, the typical data that you can get in terms of your traffic volumes is a very typical data that you require for almost any cost-benefit analysis relating to roads and transport. But with flooding, you need a little bit more, and that in relation to, for example, we've got annual average time of closure. So what is that? So that is the average time that the road is closed per year. So, for example, you may have a road that closes every 10 years, and it closes for 10 hours every 10 years. So that would give you an average of 1 hour a year of closure time, approximately. There's some calculations around it. Could give you slightly, but that's just the general picture. The average duration of closure is also another important element to it as well. So the average duration of closure, an example of closes once every 10 years for 10 hours, would then be a 10-hour closure, and that would be your average duration of closure. And that's important as well because the longer the closure, the difference in behavior in terms of user behavior. Short closures, people may be more likely to wait for it and not actually change their activity. So if you have, let's say, 1 hour closure every year, you'd just wait it out. Whereas if you've got a significantly longer closure, then they may be more likely to engage in other activities. Or if there's a diversion route, they may actually take that instead. I'm talking about diversion routes. You need to identify if there is a diversion route and how long that diversion route is. And also, is that diversion route subject to flooding? And if it is also subject to flooding, does that flooding coincide with where your existing route floods as well? Or is the timing difference? There's a lot of things you need to look around diversion route, which is actually quite critical. And as well as that, you need to have a look at the parameters and the road parameters of these diversion routes. So do they allow for all vehicle types, for example? Are these roads sealed? And what are the costs of actually traveling on these roads to the actual users? And are there different diversion routes for different vehicle types? You need to know the capital cost of the project, fairly typical, and also your maintenance costs. And that relates to damage caused from flooding as well as just your regular maintenance as well. In addition to this, what else do we need as well? So you'd need to have your traffic volumes for the whole network, or let's say the whole network, but the relevant network. So which would include your diversion routes. You also need to get the average annual time of closure for those roads, and also the average duration of closure for those roads as well. Another thing that's not commonly discussed in cost-benefit analysis, and that's the average recurrence interval. So how often do these floods actually occur? So are they occurring every year, every 2 years, every 3 years, or maybe 3 times within 1 year? And how do we define that as well? And there's also a certain level of immunity for like bridges, for example, use it in terms of the Q. So if it's like a Q50, it means it floods every 50 years. Or if it's a Q10, it means it floods every 10 years. Or you could even have a less than Q1 or Q2, which meaning that it floods on a yearly basis. And that data is very relevant as well. Also, what's important as well is people's willingness to pay in order to make a journey. Some journeys may be considered critical, so therefore they would opt to take a diversion route if one's available, or may even take another form of transport, like you may want to go by boat or even by helicopter if these trips are absolutely urgent. And in the case of emergency, if it's choice of life or death, that trip has to take place anyway. There could be other trips that are really not that important, and there could be alternative activities. So there's going to be quite a wide fluctuation in terms of willingness to pay for a particular journey too. Also, another thing to bear in mind is the type of floods. Are we looking at anticipated floods? In terms of, are they seasonal floods? Are there closures that happen every single year that can be planned and worked around? And trips are far less frequent during that time? Or all these floods, maybe the floods are unanticipated, which is more difficult if you have flash flooding that just occurs out of nowhere. You expect these to be less frequent, but the cost of an unanticipated flood could be quite substantial and quite substantially higher than your anticipated floods that you get seasonally as well. So it seems like we actually have quite significant data requirements to actually do a real thorough analysis of a flood immunity project. So with that in mind, what are the data sources that could be available to us in order to actually, get this data, meet these data requirements? So look at something known as TARS, which is the Traffic Analysis Reporting System, and that contains quite a detailed breakdown of the traffic volumes on, I think, all of the state and federal roads within Queensland. And you can actually, it breaks it down into, I can't remember the vehicle types, I think it's more than 10 vehicle types there. So that is actually very useful, and like I said, that is for all those roads there. So it doesn't tell you how they'll divert, but it gives you a good idea of what vehicles are using what roads. Another thing that we call is ARMAS, or available in what we call chart view, and this picks up almost all of your road details. Like you can get out of that the width of the road, the number of lanes, the surface of the road, even the maintenance that's happening and the occurrence of this maintenance. So it's actually very useful information when you're doing analysis. We've also got digital video road, and this actually connects in with chart view. This is another transport and main road software, and you can actually see the road itself. It's like you're traveling in a vehicle. It's much almost like the Google van that goes around, for the Google Maps. This looks at the roads. You actually get to see the quality of the road and the surrounding environment. And you may actually get some additional information by actually having digital video road, which you can't get otherwise. There's hydraulic reports. These are useful in terms of telling us how frequently the area floods, how long the closures are, how long the roads are underwater, submergence. There's also corridor studies that gives us an idea of the entire corridor and the closures in relation to that, and that can feed into our network. There's also the Bureau of Meteorology, which I mentioned earlier, where we got information about rivers and the frequency and the flooding of these mirrors. There's Google Maps, which is available to all of us, and Google Earth, and that also is very good at supplementing some of this other stuff as well, because you get a very broad view of the roads, and you can go to other roads that maybe that digital video road can't quite get to, and you have a very broad view of the surroundings. So Google Maps can also help you in terms of distances between various points on the map, so that gives you a better idea of your diversion routes. There's also the Austroads unit value update reports. So this gives you inputs into the analysis such as the value of time, and also as well as the updated road user figures as well in terms of tire wear and fuel and things like that. Since this presentation, that's been actually updated, and I've got something known as ATRF that actually contains all of these figures. You can also go further afield and have a look at journals and newspaper articles that would have picked up stuff that's not necessarily documented or recorded as data, but this gives us some good idea about, from the point of view of the public, for example, there's some public input into some of these newspaper articles about the extent of the flooding and how that's actually caused disruptions. And of course, as well, you can go to the Transport and Main Roads regional offices, and they also have additional information that's not necessarily within the databases. And also you have people working there with first-hand experience of the floods, and they can actually provide more information, which can actually go into your analysis. So once we've collected all this data, we have all this information, now we've got to come up with a methodology and how we can actually use this data to actually evaluate the benefits. As you can see here, we've got the Swedish chef. Since then, I wasn't actually vegan at the time. I'm actually probably a bit more opposed to this guy now with this chicken. At least it's a happy chicken. Let's just hope he's not trying to cut it up, hey? For flood immunity projects, it's actually quite critical to understand if there's any interrelated projects. So with, let's imagine you've got a link and you have flooding occurring in 3 places, and there's 3 projects that are fixing each spot. You have to bear in mind that you can't look at each project individually. So if the road closes for 20 hours in one spot, that's fixed up. You can't just say that the road is now open. There's no closures, because there could be closures of 30 hours or 40 hours further down the road. So fixing a 20-hour closure problem will have very little benefit just for maybe that little local area, but for not the entire link. So it's worth looking as well, if you've got 40, 30, 20-hour closures, that maybe there should be more focus on the 40-hour closure than possibly the 20 or the 30, depending as well in terms of where the diversion routes fit in. That's also important to look at the wider network. And also there could be projects on those other roads as well. So for example, there may not be a viable diversion route at the moment, but because of another project that's underway on that diversion route, the diversion route actually improves dramatically, and maybe your initial project you've got here may not become so critical anymore. So you could have a situation where the road's closed for several days, which is quite bad, but now you've got a diversion route that maybe will only take another hour or so. So where compared to not being able to travel at all. So it's very important to be aware of what's happening on these other roads and the diversion routes, and further on the individual links. Here we have a few maps of rural Queensland. As you can see, there's not many roads really. This is looking at a very large area. You probably can't see the scale here. We're talking about hundreds of kilometers where you actually only have a few options to travel. So if one road gets cut, you may have to take a very long diversion route. And this is true for all of these, whether it's the far north or Fitzroy or central west or southwest Darling Downs region, that there's so few alternatives that floods can actually be very, very costly. For states that have a network that's got more roads, again, it's higher population and things like that, the road closures are probably going to be less costly in the sense that you don't have such long diversions. But for Queensland in particular, these long diversions can potentially be very costly. Or in some cases, there may not even be a diversion route, because you may have your 2 roads that access a particular area, both of them going under at the same time. What I've always found to be a useful way of approaching, or any analysis for that matter, cost-benefit analysis, is actually to draw just a quick little, what we call a mud map. So we just very briefly just draw the alternative routes and stuff like that, and figure out exactly what can be used and what can't be used. So like we've got here, for example, in the first one. So it looks like it doesn't seem too much of a problem going from B to C. You have the original route and you've got a diversion route. That isn't much longer, but if you take it into the broader perspective, you have a look at this other map here. So you've got a number of bridges that go under fairly frequently. So it's trying to find which route is actually the best alternative route to use if that does exist. So if you've got some of the really major floods, potentially the whole network goes down, but some of the minor floods, you can actually see there's possibly quite a few decent alternatives. Like you've got the blue lines and the green lines, and most of those are going to stay open because they're So the ones that are more problematic are those that are surrounded by frequently closed, like you can see town D, I think we got here, and that's actually got two closures either side, one between C and D, one between D and B. So fixing up one of those is probably going to be more of a priority than maybe fixing up somewhere for like A, for example, that actually has better access, either going from E or from C. So it's worth just setting up and drawing out these little maps just to have an idea of where your benefits are most likely to sit. What I'd like to look at a little bit more closely now is actually road user behavior and how people behave during a flood. So I haven't gone into too much detail, but we generally assume if a road is closed that the user would do one of three things. And that is either for A, wait for the road to reopen, B, take a diversion route, or C, engage in some alternative activity. But the question is, how do we actually know that and how do we actually calculate that? So I've come up with two approaches here. One is the exogenous approach and one is the endogenous approach. So the exogenous approach is basically it's collecting data on what seems to be typical behavior. And that would be, you can get that out of the region if it's available. Normally there isn't too much around, but again, you can look at interviews and stuff, what people have been typically doing during floods, and they'll be able to tell you, are they waiting for it to open? Are they doing other things, or what other activities are available? So that's one way of going about it. But if this data is not available, then you can go with what I call the endogenous approach. And it's actually calculating it through the model. And how you would do that is you calculate the costs of diverting if there's a diversion route. So you may have an extra, let's say 300-400 kilometers to travel. What would that be in terms of cost of time? What would that be in terms of cost of, the vehicle, in terms of your vehicle operating costs? And also, how does that vary between different vehicle types? So you have some of the more urgent journeys that time is going to be very, very precious. And some, maybe if you're what I call the grey nomads, it may not be as urgent. So those values are going to be different. And then we compare that diverting in terms with what happens with waiting. So that is based almost purely on time. How does that value compare to waiting? So will waiting be favored over? If time is very, very precious, then you probably wouldn't wait. You take the diversion route and just bear the additional costs of the vehicle operating costs. And the other option is alternative activities. Is there an alternative activity? Again, it's difficult to gain information on that, but if there's very good alternative activities or alternative locations, then waiting or diverting may not be a problem. It all depends on how critical it is to actually reach that particular destination. An endogenous approach does that using the numbers that we can actually get out of our databases if there isn't any additional information that we can actually get out of the community that we consider to be reliable. So bearing that in mind, I think the endogenous approach is generally more time saving and can give you a fairly good answer, whereas exogenous could be quite unreliable. But again, I wouldn't completely ignore that. People on the ground, people that experience the flood events, they have some quite good knowledge of what's actually happening and stuff that we can't necessarily pick out in the numbers. So both these approaches are definitely worth looking at and definitely worth investigating when you're doing flood immunity CBA. So here we have some of the equations that can be used to calculate your not traveling time or your diverting and your waiting time. So this is a little bit of what I explained just now of the previous slide. It's actually trying to come up with the minimum cost. So what is your cost in terms of what is your perceived cost of diverting, and how does that compare with your perceived cost of not traveling, and also with your perceived cost of actually waiting? So you take the minimum of each one. So for example, and this also as well, I'm going to explain, also depends on the timing of when you actually arrive at the flood site. I'll cover that with a few graphs later on, or I'll call them graphs. Yeah, I'll call them graphs later on. But yeah, as you can see, all of these come down to the minimum. So what is less? So is it less? Does it cost you less to divert? If it does, then you will divert. Also, as you're getting closer to the time that the road reopens, then diverting cost is not going to look as favorable as compared to actually waiting. And the same goes again for those that are not traveling. What is the difference between what you gained out of reaching that location? So for example, I don't know, let's say you go to a particular location, you get $200. It costs $100 to get there, let's say. So that's a gain of $100. Whereas there may be another location that takes normally $100, costs $100 to get there, but you're only getting $130 back. So you gain $30. So in a sense, if your cost of traveling goes all the way up to $190 and you're just getting, let's say, a $10 benefit out of reaching your location, then you'd probably go to your alternative location and get $30 worth of benefit out of it. That kind of makes sense to you. Anyway, this is basically what these equations are trying to tell us and how it's calculated. Okay, so I'm going to look at the costs in a little bit more detail in terms of how that affects road users and how we can actually come up with, I guess, a reasonable number. But again, it's held by a number of assumptions. So let's have a look at cost of diverting. So you can see this big red square. So this is assuming that we've got a reasonable fixed cost for diverting. So the diversion route is, let's say, is always going to be, let's say, 300 kilometers. It's going to use about the same fuel consumption no matter what time you travel. And it's going to take about the same time, assuming that, these may be rural roads or whatever in this case. We're not going to get too much congestion. So we've got that there, and that gives us costs between, A and C. There we go, A and C, and I think we've got A and B. This is divided the costs up, I think, into what is perceived and what isn't perceived. But for this matter anyway, we'll just assume we've got the big red square there, which of course doesn't really change. And it's not dependent on how long the closure is. So the closure could be 10 days, it could be 1 day. This would be exactly the same cost because you're taking the diversion route, which is not affected by how long the road is closed. That's why it's that big square. So you look at the x-axis, this is the number of road users, and this is where cost of not traveling comes in. So below that line, y to x, that we got there, so that will be your costs of not traveling. So as you can see from C to D, the cost of diverting is actually less than not traveling. So those users between C and D would rather divert than not travel. And then we get from D to X, these are the users that have a very low cost, I guess. They have good alternatives, should we say, good alternative activities they can engage in. So the cost to them would actually be fairly low, and the cost of diverting would actually be higher than their costs. So those are the ones, not getting an awful lot of benefit out of reaching their destination. So we'll talk about those in a moment. So that would be the benefits of not traveling. If you look along the z-axis, you can see that you go from D up into about E. So this is looking at it in terms of duration of closure. So at the beginning of the closure, you're going to have vehicles are going to be more likely to want to divert because the waiting time is very long. But once you get to the waiting time where actually it's going to open up again, I'm assuming then that there's some knowledge about when the road is going to reopen. Then at that point in time, you're going to have road users switching to waiting rather than diverting. So for example, at the beginning of the closure, the cost of waiting could be, let's say, $500. But as you're getting closer and closer to the time it opens, that may go down to $100. And if your diverting costs are more than $100, and then waiting then becomes the better option. So that leaves us with that square, that rectangle, shall I say, is actually your cost of diverting. So we're going to now take a look at the total cost of waiting. So waiting costs come in once we've got close enough to the opening time for vehicles to consider diverting not a viable option. Of course, if no diversion routes available, then waiting becomes basically a viable option from the very get-go, or if diverting is too long, closure is short enough anyway. So, we're talking about now, it all depends, I guess, on how long the diversion route is and how long the closure is. But you get to some sort of equilibrium where waiting is actually preferable to diverting. And also bearing that in mind, you also factor in as well that not traveling is still an option too. So you may have those that would have chosen not to travel when there was plenty of time left. But now, because you're getting closer to that reopening, some of those that previously did not want to travel will actually now rather wait than not travel. And that gives us down here our little turquoise, I'll call it some turquoise triangle there in that second figure there. So the combination of these two, the green triangle and the turquoise triangle, that would be your total cost of waiting for that particular closure. And I'll have a look now at what we got for not traveling. So for not traveling, you're faced with two scenarios. The first one is when diverting seems like the optimal choice, but the cost of not traveling are actually less than diverting. So that's your yellow area there, and that yellow area is relevant right up until you get closer to that reopening of the road, and then the waiting costs start to drop, and therefore you don't get that full area out there. Instead, you get the turquoise area, which would be very similar. There's kind of a split with your waiting, so there'd be some users deciding not to travel and some deciding to wait. So you'll have some of those that are almost indifferent between traveling and not traveling, and that's where you get into that little purple area of those ones. Sorry, not purple area. That little turquoise area, getting down to between O and P. So again, those two areas, you combine them together, and that will be your cost of not traveling. And that's basically what those equations were showing you just now, a few slides back. Also, it's worth looking at the paper. The full paper has a full explanation of how the calculations are done. But I've done it out in these little three-dimensional graphs, because these three-dimensional figures, just to give you an idea of how it all fits in. So, like I said, just a quick recap, you've got the diverting, which is your big square, which is more or less a constant that's not linked in order to how long you've got left of the road to open. Your waiting time, which comes after that once you're getting closer to reopening, and more vehicles are switching to waiting rather than not traveling, because that becomes a lower cost. And also you're not traveling. When you're not traveling is actually less than diverting, and then later on it's still less than waiting, but there'll be some switching to waiting because the waiting costs are falling more and more as you get closer to opening. And eventually you almost wouldn't have anyone not traveling at all when you get down to that last half hour before the road reopens. But this is all hinged on them actually knowing when the road is going to open. Again, that is quite a big assumption. And all of this is an input into what I call the endogenous model. So it looks fairly complicated, but once you've got the mathematical equations sorted out, it just goes into a model and automatically calculates it by itself. So what's still not being picked up, and there's a few, I'd say, costs and potential benefits of improved flood immunity that's not being covered. One of them is safety, and that's quite an interesting one as well, because when the road is flooded, the road can actually break up and can more or less disappear, and that's not necessarily visible to vehicles crossing. There are some people that will still want to cross floodwaters, and without knowing it can actually end up being in a fatal accident because they're no longer on the road and they get washed away in their vehicles. And for almost every major flood, at least you have a few people dying because of these accidents. So that is, again, quite a cost, and we can reduce that. That would be great, and that's another benefit of improved flood immunity. You've also got as well the wider economic benefit, and I may have mentioned it briefly earlier, but if an area is consistently getting cut off because of floods, there could be a loss of economic activity as it's not become a reliable centre for actually for business to actually work and trade there. If you're talking about several floods a year, if you improve that immunity, you could actually see a growth in the number of vehicles and a growth in activity that might not necessarily get picked up. And it's difficult to know, because if it's consistently flooding in that area, what is the level of deterrence to businesses going there? I guess surveys and all can be taken, but it's one of those things that you're most likely going to find out once the flood immunity is actually improved. So I'm now going to have a look at a number of different models and what sort of results they're producing when we look at flood immunity. So we've got the model here, which is Transport and Main Roads, call it their main model, and that is CBA 6.1. I've also got a rapid flooding analysis model, and I've got another one which is an endogenous demand model. So we can look at the results produced by these models and see how they differ and why they differ. In order to test these models, I've got a case study here just to have a look at. This is of a rural bridge out, I'm trying to remember where it was now. It was further up north, so you don't have very high traffic volumes. In fact, we've got a traffic volume or average annual daily traffic of between 200 to 300 vehicles, and there's not particularly great access around there, especially during the major floods. And also there are closures as well, fairly frequent, from up to about every 2 years, and these closures for about 15 to 20 days, depending on the vehicle type. There's actually one that I didn't mention as well, a benefit I should mention a little bit earlier, but there's what we call a dryback period. So for heavy vehicles, they may not be able to use the road for a number of extra days because the road has to dry out, and potentially heavy vehicles going on a very wet road with saturated water can cause quite a bit of damage. So the closures for the heavy vehicles could actually be a little bit longer. So bear that in mind. So this would be our case study where we test the models. For anyone watching this video using their mobile phone or small device, you're probably going to have a hard time seeing these numbers. But I'm going to highlight the main numbers anyway from these models. So what we got here, we got CBA 6, as I mentioned. We've got the endogenous model, that was the rapid model, and also the proposed model. This is one that I'm proposing with some of these additional features in there. So cost-wise, they will produce pretty much exactly the same in terms of treatment of cost. be putting the costs in their respective years, maintenance in their respective years, and then discounting them, and plus whatever residual value as well. Bear in mind with bridges and things like that, you're generally going to get a residual value because their life exceeds the evaluation period. So it may have a life of 50 years, and our evaluation may only be for 30 years. So let's just have a quick look at the benefits here. So cost benefit analysis CBA 6 gives us only about $760,000 worth of benefits. The endogenous model is even less, $343,000 worth of benefits. And the proposed model gives us actually quite a high number of about 6.2 million. So as you can see, it's significantly different. So why is that, and where are those differences occurring? So what is actually being picked up with this model that's not being picked up anywhere else? So you go down the numbers, you see there isn't too much difference between some of them. Again, you have to bear in mind that CBA 6, CBA 6.1 doesn't have an endogenous element, so we're using exogenous. So this is information provided by the region, and then that's being put into the model. So you're going to have a different number of road users diverting and waiting depending on that. Whereas the endogenous model is going to be more of the optimal level. So you'd expect it to be a little bit lower because people are going for the lower cost solution. Whereas with CBA 6, you could be using, they could be all diverting for the entire period, for example, whereas endogenous model, they only divert at the beginning, then switch to the lower cost waiting. So actually that will pull your costs down in your base case, should I say, and then that actually, with lower costs in your base case, you actually have less benefits. So you'd see something similar with proposed endogenous models, but the big difference here is actually the not traveling, and that's interesting because that is where it gets a little bit subjective, because currently within the models that you have is that there's no value placed on not traveling. So you need to assign a value to that. And assigning a value to that is basically what holds all the analysis up. And in the case of very long closures, not traveling may in fact be your only option because waiting isn't viable. There are no diversion routes because they've been cut off. So engaging in alternate activity is actually your main option because you just can't get to that location. So you need to put in some assumptions around what is your cost of not engaging in that activity, and that's what had been done with this. And the paper will explain a little bit more detail exactly how this not traveling cost was actually calculated. But most of those benefits come from the floods with the very long closures, the more infrequent floods. Whereas your more frequent floods, there's alternative action that can be done and it can be more adapted to. And that's where you get the significantly higher benefits, which produces a net present value of greater than 0, and you've got your benefits cost ratio of greater than 1. Whereas the other two models are giving you negative net present value, and your benefit cost ratio is actually below 1. So that is quite interesting as well. But yeah, you have to look at the paper. That will explain in more detail exactly how we came up with the parameters for not traveling. So that should be a good read if you want to read that. Here I have another example, and this is going back to the methodology I explained just now. And this is looking at in terms of a network. So I showed a diagram earlier on, and that was I pointed out you had town D, which was isolated, more or less, of the flooding. So it comes down to a choice of whether you want to upgrade the bridge that's on the link DB or upgrade the bridge which is on the link CD. And I actually evaluated the benefits and the costs for upgrading either one of them or upgrading both of them, as you can see here. So you've got the cost, assume the cost to be the same. So you can have the total for doing both, or you can just look at each one individually and how that actually calculates out. As you can see, there's actually benefits of actually upgrading both bridges because you've got traffic going from either side entering into town D. And that gives us a net present value of about 2.5 million compared to both the other two are getting net present values of actually just under 1 million. And also you've got the higher benefit cost ratio as well of about 1.7 compared to the doing either one of the options as 1.5. So as you can see, actually upgrading the two bridges is actually greater than analyzing the two bridges individually and then summating it, because you have those additional benefits of having access for both of the bridges. And also bear in mind as well that you can now use the route, what is it, B, D, C, or whatever, and that can actually become a diversion route for other areas when the flooding occurs. So there's a lot to it, and that's why having a network approach gives you a more fuller picture of actually how cost-benefit analysis can actually be used to actually get a better outcome. So it's possible that, you know, the combination of the two bridges may actually give you less benefits than just doing one or whatever. It doesn't give you the sum as we've got here. So it's worth looking into what those routes potentially can be used for. Okay, so what is the limitations now of using the approach described in this paper? First off, it initially will be a little bit difficult. There's a few areas that need to be investigated a little bit deeper than initially. So it could be a little bit time consuming and requires a little bit more experience because not many people have experience in doing flood immunity cost benefit analysis. Data is probably going to be a little bit more intense as well. As I mentioned earlier, that there's quite a few additional data requirements, and that is going to take a little bit of time to actually collect that. We have the sources there, but for flooding, it's often the case that that can be a little bit unreliable, the sources for some of these, and you don't get a complete picture. And probably the biggest limitation of all is actually coming up with the cost of not traveling, because almost every user has a different alternative than actually making the trip. So to come up with a number on that, a reliable number, is going to be very difficult. As you can see, this whole analysis from the results just now actually relies very much on knowing what the cost of not traveling is, and that is going to vary very significantly. And that means actually investigating what the alternatives are for the majority of the vehicles. So in short, it's really going to be quite a time-consuming exercise. But given the importance and also the amount of money that's being put into actually upgrading bridges and improving flood immunity, it seems very worthwhile to actually have a very thorough analysis. And also in the long run, because you'd be looking at networks in a sense that some of the initial costs of maybe getting through the first few projects, you may realize that there's quite significant cost savings as some of the other projects may not become necessary, or you'll be able to find out which project's actually more crucial. So for example, you may have a bridge on a road that only has 100 vehicles, and it may seem fairly insignificant using traditional approach, which is driven by vehicle numbers, when you realize that that bridge is actually quite critical for other roads when they flood, because that road becomes then a very important diversion route that doesn't necessarily get picked up if you don't look at it in terms of a network. So you can see there are a number of limitations, but personally I think developing this model has actually got far more benefits and limitations to it, and it should be a definite way to progress in terms of looking at flood immunity. Okay, so this takes me to the end of this presentation. This is, for me, is thought of quite fondly because this was my first conference paper. As you can see from the series, I've actually worked backwards. So I started with the more recent papers, going back to 2016 and ending up in 2011 with this paper here. So this is pretty much toward, I don't think I have any more papers. Well, I may have another one that I'm going to present, which is actually going to look at a journal article I did and wasn't actually presented in the conference. But anyway, I'll get back to this paper, what I was saying. So what are the key points we picked up? So it comes in critical in the sense that you've got to be able to identify as many benefits as you possibly can. And also you've got to identify how you can obtain the data to be able to evaluate those benefits and how those benefits can actually go into your cost benefit analysis. So you seem to have done that, and we also have the sources behind that. So there's been quite a bit of effort that's gone into that. And I think the biggest thing that comes out of it, and this is a theme actually across a lot of my papers, is actually look at it in terms of a program or in terms of a network. You have a network, you can actually see the bigger picture a lot better. And this is not just for flooding. Flooding can be incorporated with a lot of other ones as well. You could have safety projects that incorporate flooding elements, or they could be flooding in relation to possibly capacity issues and how some of that could be relieved. And it can work them all in together. So a network approach or a program approach, I think, is a very good way about going about anything in terms of planning and in terms of analysis and all of that. I think that's a good step forward, and this is something that I've covered on many of my papers. So anyway, I hope you've enjoyed this paper, and yeah, I'll probably have, I think, at least one more presentation relating to my conferences. This is not, like I say, this is not so much relating to my conference, but more to an actual journal article that I wrote. So I'm not sure how I'm going to take this at this moment. But thank you again, and yeah, I look forward to presenting more of my stuff.
If you like today's video presentation, just click the like button and the subscribe button. If you want to find out more about today's paper, just go to my website at spectrumecons.com and you go to the research paper, just click the link there and you'll get the paper in full. Again, thank you for listening. Goodbye.